recall what the hybridization is and geometry, right? So it's basically going to be the case for like each time when you have, okay, well, hybridization on this carbon is like sp2, geometry is a trigonal planar, right? Then we'll have a new hybridization for the carbons with the asterisks and the new geometry respectively. So, but again, you saw the table of geometries and hybridizations, so potentially it was helpful. So maybe let's try to kind of like recall that and then see what happens here. All right, so great, we have some responses coming in. So good effort, thank you for that. So and then it looks like we have sp3 everywhere. So yeah, those ones will become now sp3. And now the geometry will be tetrahedral. So tetrahedral, great. So just kind of like make sure that you are clear here. So this is indeed tetrahedral. So those two carbons tetrahedral. And then these two will be trigonal, right? So trigonal planar. So that is true for the like sp2 hybridized carbons, which those are, right? They are sp2 hybridized, and these two carbons are gonna be sp3 hybridized. So yeah, just kind of some clarifications, and then yeah, we'll be in good shape. So here you can also say, well, we undergo a rehybridization, right? So it used to be like sp2, then it became sp3. So yeah, you rehybridized your carbons. So yeah, but that's pretty much it. So then at the end of the day, we are going to make alcohol, right? As we can see from this. So from the like practical perspective, it's like useful reaction. So because you can potentially like take some kind of like alkene, right? And then make an alcohol out of that for whatever reason, like from the, let's say, synthetic perspective, right? So that's just going to be like used maybe in industry, right? So if you go on and then start working in the like organic chemistry lab, or maybe some kind of pharmacy lab, right? So you might see this reaction quite a bit. So it's pretty fundamental, quite easy, right? So oftentimes, maybe let's say from the like organic, from the plants, you'll be able to derive some sort of like alkene-based compounds, right? So they will have the alkene functional groups. So then in the responses to the challenge assignment, somebody was talking about how the OH group can be used to facilitate the solubility of the like drug or something like that, right? So then, yeah, you might be like, okay, well, let's turn the alkene to the alcohol, and then this like plant-based compound with some sort of change in the functional groups can be like better absorbed by the body because it has this like OH group, right? So yeah, that's just kind of going to be some kind of like drawn example, but can potentially be used in the future. So who knows? So now then what else? So this reaction also follows the Markovnikov's rule, specifically when we look at the cases, when we have different number of H's attached to the carbons in the carbon-carbon double bond, right? So that's when this like Markovnikov's rule kicks in. So as somebody like several people, I think, drew that on the board for like the reaction with HCl or HBr last time. So this is going to be the same principle, right? So the same principle will be followed, except instead of HBr, you have HOH, right? So literally kind of like only one minor change happened, but the rule still will be followed. All right, so now here we go. So that's potentially going to be a good example of how to use this rule in this case, because if you take a look at those like skeletal structures, we'll be able to see that to those sp2 hybridized carbons. I'm just saying sp2, and now it's going to be your responsibility to figure out which ones are sp2, right? So because, well, several people do know that at least, so which is good. So, but for now, let's just be trying to catch up with that, right? So which ones are sp2? So which ones are sp3, for example, because you can find both kinds here. So Now let's maybe like convert those skeletal conformations or skeletal drawings, structures, right, into the expanded ones. So we can do that, right? So perhaps it's going to be a good idea to pay attention specifically to this double bond here, right? So that's kind of like what we're looking at. Sorry, that's the marker. So maybe like this region, right? So the purple one. So here we go. So let's redraw that. So yeah, the ring can be redrawn to a large extent. So, but now I'm going to like realize that kind of like on the left here, sorry, that's the wrong one. So on the left here, so we have the carbon, and this is going to be another carbon, right? So with the double bonds. So yeah, that's okay. So let's just modify this structure a little bit, and that's what we are going to obtain, right? So as we remember, we imply some things such as hydrogen atoms, and then at the end, so like on the like right side of this purple bubble, we have the carbon, right? Carbon already possesses the two bonds, right? So consequently, whatever is not shown is H's, right? So how many H's can we like show maximally? So it's going to be only two of them. So, and that's it. So that's going to be your kind of like sub structure, so to speak. Because it's going to be the hybrid kind of like between the expanded and the kind of condensed structure. So, but that's where the reaction will happen, right? So that's why we try to expand this region, particularly like CC double bond. So now we have here our things, right? So H2SO4, as you can like figure out by exclusion, that's going to be your additive or the catalyst in this reaction. So that's number one. So number two will be H2O, which is going to be our actual reactant. So well, for your review already purposes, you can show it as such, right? So that's your H2O representation because it has this kind of like H2O structure. And you can see this clearly, the HO bond, which we draw. Why? Why do we draw that? Because we want to show that it will be kind of like broken, this bond, right? So then we can also show that this like pi bond will be broken here, and that's it, right? So then we are like on the way to show, let's show the conditions as well, and then we can demonstrate our products finally. So here we have the like Markovnikov's rule like in effect, because so if you look at these two carbons, so we have carbon number 1 and carbon number 2. So which one has more H's? So that's the question. And where will the hydrogen go, right? So this hydrogen with the blue asterisk. So where will it go? Okay, so let's just ask this question. Where will the blue hydrogen go, right? So blue for the blue asterisk. So hopefully it's visible color-wise. So that's the question. So where will the blue H go? Okay, and why, right? So that's going to be another question here. And why? So because it's related to this Markovnikov's rule, right? So to which carbon basically will the blue hydrogen go? Carbon 1 or carbon 2, and why, right? So, and then the expanded structure helps here because it kind of like shows the clearly the number of hydrogen atoms attached to each carbon 1 and 2. Right, so that's going to be another question to think about. Perhaps a little bit of the review from Tuesday. So, yeah, the rule and such. So this, yeah, this is where we are at, basically. Markovnikov's rule. So it's going to be like a good idea to remember that one for the upcoming exam at this point on March 6th, I think. So just 4 exams, again, general announcement. Please take a look at the schedule, right? Some people couldn't find the schedule. I made it a separate file, right? Back in the day. So, but again, still, like, please take a look at that, right? So it's on Brightspace. Go to content, go through the modules. You will see like the like homeworks there, by the way, right? And then other things such as like presentations, recordings, whatever else there is. And specifically, you will see the syllabus and schedule module, and then just maybe print out the schedule, put it on the wall, and then you will see the schedule of exams. If we have any changes, hopefully we will not have too many changes to the schedule, then it will be like announced in the announcements, right? So you will be in the loop. So just kind of like read those and then yeah, we'll be fine. All right, so now let's take a look at the question answers here. All right, so looks like what do people say? Okay, 1 or 2. So far it's unilaterally, it's carbon number 2. So because there are more hydrogens. Okay, that's it. So yeah, indeed. So this carbon has 0 H's, this one has 2. So then this blue hydrogen will go here, right? And then we are going to show our product, right? So which in this case will be cycloalkane. So yeah, basically this like cycle will stay. So then we are going to have our carbon, right? So this sigma bond will stay. So then we're going to obtain our methyl group, by the way, right? So CH3. And then the OH group, this will be your like blue. This is blue, now it's brown. So, but yeah, it's okay. So, and now finally you are going to show your alcohol, right? So that's what it will be like. So tetrahedral, all good. Rehybridization took place, and now you have the alcohol, right? So another way to look at this kind of like Markovnikov's rule is that you can think about the other group, which is like opposite to the hydrogen. It's either OH if you have water, right? Or HCl if you have like acid. So then people say that the OH or chlorine group, depending on your initial reactant, will go to the more substituted carbon, right, with less hydrogens. So that's another way to look at this rule. So, but anyway, so that's our alcohol here. So then you can take a look at another example. So maybe let's take a look at this guy here. So in this case, we're going to have couple carbons as well, 1 and 2, right? So then if we look at this, so carbon number 2 again, so in this case, we'll have less hydrogens, right? So carbon number 1 will have more hydrogens because it will have 1 hydrogen as opposed to 0 H's on carbon number 2. So consequently, that's where the hydrogen from the water molecule will go, right? So here we can just show the abbreviated version of that. So because why not? So it's going to be good eventually for the skills. So, and then here we go. So here you'll explicitly show the hydrogen, I mean, not the hydrogen, but the rather OH from the water, right? And then on carbon number 1, which has more hydrogens, we'll have the hydrogen from the water. So let's put it this way, right? So, and then OH from the water will be on the more substituted carbon, or the carbon number 2, which has 0 hydrogens, right? So we are going to put the OH here. So yeah, that's it. That's going to be another example. So again, the hydrogen, which is blue from the water, came to carbon number 1, which has more hydrogens than carbon number 2. Carbon number 2, 0 H's. Carbon number 1, only 1 H. 1 is more than 0. So, and then, yeah, here you go. That's going to be your like final alcohol product. All right. So now let's see if it is time for activity 2. Okay. So we're going to start actually backwards a little bit. So we are going to take a look at activity number 3. So because it's already kind of a review at this point. And then you have the bonus question. So for maybe the same individual or the second individual who can show that. So the alcohol dissociation, right? So, but it's going to be kind of a step-by-step reaction, if you will, right? So you'll need to show the hydration process of the alkene with 8 carbons. And then you need to show the dissociation of the alcohol, right? So think about that. So, but you can do them all, or maybe just one, and then somebody else will do number 2. So, but here you go. That's your like chances to score extra points as usual for the second exam at this point. So for activity number 3. So now it's your turn to like do some practice. And yeah, so you can go for that if you want, right? So we have 8 carbons, alkene, and then we need to show, we need to make sure that kind of like follows the Markovnikov's rule, right? So basically, one carbon will have to have more H's than the other. So in this double bonded carbon piece of the molecule, and then we need to show the hydration, right? So what's hydration? So that's what we have seen just now. So 8 carbons in the alkene. So yeah, if you want to try. So yeah, let's go at least do activity 3A, right? So then we'll get to 1 and 2 later on. So, but for now, let's take a look at number 1. You have it. All right, great. So you have the markers here and the paper. So yeah, okay, let's take a look. All right, so let's see what we can come up with, right? So it needs to be like a specific alkene. So maybe it's going to be like, as we saw, 0 versus 2 H's, right? So that's different numbers of H's. Maybe it's 1 versus 0, still different numbers, but it cannot be like CH2, CH2, right? It's symmetrical, will not work. So let's see what we have here. So this is an option, but make sure that you show the hydrogens, right, everywhere. So let's just have it as a habit, right? Here you need to like check your CH3 because it's going to be too many bonds. Yeah, that's the one. So now you have the correct valence, right? That's number 1 line of defense. And then you have the different number of H's on those 2 carbons. So that's a good way. So yeah, you can clearly see that you have CH2 double bond CH. So that's going to be your thing here, right? So then a lot of the stuff will be just about like redrawing the like alkyl part from the alkane, right? Which is going to be your like 6 carbons in this like part of the chain. In addition to the 2 carbons from the alkene part. So, and here we go. Okay, well, colors are good, right? So they will show, so maybe like water used to be green, right? So if you want to like stay completely consistent, you can do that. So water will be green here, and you are making your alcohol. So the green hydrogen, which came from the water, goes to the leftmost CH2 in the alkene, because that CH2 has more H's, right? So H's to H's, and the rest will be to go into the carbon with less H. So that's it. All right. So this is a good looking alcohol for now. And now we're going to go to the next step, right? So that's a dissociation. What's going to be dissociating in the alcohol, right?
Oh, I'm going to do the right and wrong. Is that okay?
Okay, yeah, that's right. So you can do the like wrong one. So that's okay. I assume it's the red X or purple X, whatever the color is. All right, great. Let's take a look at the wrong one, right? Okay, so yeah, that's it. So these are your like options. So this is going to be the correct, right? So that's what is shown here. So hydrogen. So assuming this was like a green hydrogen, imagine it came here to the carbon with more H's. So OH will go to the other carbon with less H's. So that's going to be the wrong one, right? So yeah, because in this case, hydrogen went to the carbon here, this one with less H's, which doesn't happen, right? So, and now if anybody wants to do the dissociation, so it's also kind of like up for grabs. So you can try the alcohol dissociation, which is, again, we saw that previously, right? It's very similar to the dissociation of the water molecule, except you'll have a little bit different structure, right? So, but the OH bond will dissociate. So that's what will happen in this situation. So if you want to give it a try, so you can do that. So I think we did it already in the past. So that's the alcohol dissociation. So if not, we'll just move on, but it is yet up for grabs. Alcohol dissociation, very similar to the water dissociation, right? Like almost the same, but you have just a different tail, right? So if you like think about it, so like for the water dissociation, if we recall that, right, from the general chemistry, again, so this bond is broken. So it's going to be basically the OH bond breakage, and then you are going to have your, H plus and OH with a minus charge, right? So That's what we get. So maybe alcohol dissociation, if anybody wants to give it a try for like this, the correct alcohol, you can do that, right? So that's up for grabs. So yeah, just think about it for like several seconds, and we are going to move on eventually. All right. So we did see that in the past. So somebody did show it on the actually like also like under the camera. So yeah, it was there. So alcohol dissociation. So it's going to be 3 points for the second exam. So yeah, it's yeah pretty much here, right? So this is your proxy, right? So that's kind of going to be the basis. And then yeah, instead of this green H, you have your alkyl chain, right? So that's all it is. So you'll just have the alkyl chain instead of the double underscored with green lines, hydrogen, right? So that's all it is. Okay, so like 3 points, it's still up for grabs. All right. So anyway, so if you want to do that, so you can give it a try before we move on to the next part of this chapter. Okay, so yeah, this slide will serve as just the summary, right, of what we have had so far. So yeah, maybe you can just redraw that and print it out, and then you will have the summary of the reactions, right? So here again, you have some kind of like generic, we can say alkene, right? And we show how it reacts with the various reactants, such as like water, for example, right? So that's going to be our hydration reaction. And you have the like names of those reactions next to them. So that's very convenient. So next time you see, okay, what's, for example, hydrohalogenation. So that's when we need to like add HX, X being one of the halogens, right? So we have 4 of them so far that we can like encounter a lot. It is fluorine, chlorine, bromine, iodine. So FCl, Br, and I. So that's what the X may be in this case, right? And then you can like show maybe, yeah, like when you practice, right? Some people ask about that. How do I like practice that? Well, just kind of like do this reaction with like 4 various HXs, right? Which will be like HF, HCl, and so on. So yeah, that's going to be like a nice avenue. So then you will have your halogenation again. So you can do that with different halogens. So XX here might be, for example, like ClCl, right? Or like Cl2 molecule, in other words. So then you have your hydrogenation, which is just add H2, and then hydration, which is add water. So like for those of you who maybe like think about like the health and such, right? So they say, well, I need to hydrate in the morning, right? For example, or whilst I'm training, things like that. So same thing here. So you add hydration, you add water in the course of hydration to alkenes, right? So then maybe some more things to pay attention to. These are going to be your additives, right? Or the catalysts, such as H2SO4 or like platinum. So, and here looks like, well, there is like no catalyst. So those, because in this case, it was like discovered that those reactions kind of like go well without much of the like additives, right? So you just like mix these 2 components and then you make your product. All right, so then what else? So that's going to be another piece here. So it's about like alkynes, right? So like, again, same things will be happening. So you are going to have the pi-pi bond, right? Or 2 pi bonds in each alkyne. So that's like thing number 1 to think about. So then you'll have a sigma bond, which will stay, right, intact. So maybe you can say, okay, well, the single bond between carbon-carbon in the black ink will be your kind of like remaining sigma bond, which stays intact. So then what else? You're going to increase the number of molecules, right? So I'm going to underscore those things in green. Let's see. Okay, once again, these are underscore things. So they are called stoichiometry coefficients, stoichiometry coefficients, right? So they just show simply that we are going to like have a relationship. Okay, 1 molecule of alkyne, 2 molecules of HX, for example, HCl, right? And then that's how they are going to be attached, right? So you see HH on one carbon, XX on the other carbon of alkyne. So then if you have XX, it's pretty much like symmetrical, right? So it's all the same elements there. Or you might attach total of 4 hydrogen atoms, right? So yeah, because here technically, so like this thing here in the purple circle stands for H2. So, and then if you have 2 H2, then it means you are going to consequently attach total of 4 hydrogen atoms, right? So just again, like some things to think about. So those stoichiometric coefficients transfer over from the GenChem, and now like we need to kind of deal with them here, right? So it just shows, okay, well, 1 molecule alkyne, 2 molecules of like HCl, for example, right? So that's all it stands for. So like no big deal, I guess. So then next one. So let's take a look at the polymerization. So just kind of like a real quick concept overview. So basically what we also can do with the alkenes is produce polymers, right? So here I'm going to draw a little bit more of the like lines on the hydrogen atoms, right? So, but what's going to be kind of the practical application here? So alkene by itself might be like a very light molecule, right? So for example, this is our going to be like an alkene here, which is kind of like severely modified. It used to be CH2, CH2, but now you switched one of the hydrogens to the chlorine, and then you have this so-called vinyl or vinyl chloride, right? So that's still an alkene, so because we can, using our previous knowledge, identify this carbon-carbon double bond and say, well, it is an alkene, right? So, but it has the kind of chlorine attached to the carbon instead of the hydrogen. So now what happens next is that turns out that if you connect like a bunch of light, smaller weight molecules, you'll be able to get the so-called polymer, right? So, and the purpose here will be to produce some sort of like material that can be used, for example, for like raincoats, right? So, or maybe it's going to be the plastic bag, so things like that, right? So that's going to be the like premise behind polymerization. Right, so here what you can see is that you will see this like vinyl chloride, which will be called the monomer, right? So that's going to be just like a one piece of the chain that will become the polymer, right? So let's imagine you have, let's say, a coin, right, which is going to be like 25 cents, right? But somehow you manage to connect, for example, 100 coins, 25 cents each, and then you are going to have a chain of coins, right? So that's what the polymer looks like, except instead of 25-cent coins, you will have those kind of like monomer units, right? That will be connected. So you might connect the coins, those like in our example, 25-cent coins with some sort of, let's say, metal wire, for example, right? So let's just like think about that. But in our case, instead of the wire, we are going to use the electrons, right, to make the bonds. So that's all it is in terms of like polymerization. So again, so if you want to show the pi bond, which you told me is going to be kind of like broken in the course of the chemical reaction, that's what you will see here, right? So let's say the sigma bond will be shown with the blue electrons, right? So they will stay in the course of polymerization, right? So, but if you take a look at the red electrons, they will split, right? So basically, this bond will be broken right here. And now you are going to have the like red and red electron on the side, right? So that's going to be like the one of the things behind polymerization, right? So this bond will have been broken. That's your pi bond. And now those electrons kind of like look outwards, right? So, and the reason here is that they will be able to connect with the same molecule, maybe like 100 times, right? So basically, if you imagine, let's say n will be some random number. Let's make it 3, for example, right? So, well, we can show how the polymerization will work, right? So that's going to be based on our number of monomers. Let's say if you start with 3 25-cent coins, you want to connect them, you will make a polymer, right, of the coins, or from the coins, rather. So, but same thing here will happen, but with the molecules, right? So let's say you are going to have three molecules of this modified alkene, right? So like you'll have like three molecules of CH2, double bond, CH, chlorine, right? So we agreed that we are going to break this bond here, the pi bond, and then now we're going to connect those three molecules three times, right? So what's going to happen will be something like that. So I'm going to show it here on the second line. So we'll have CH2. Sigma bond will stay CH, chlorine, right? So then you are going to draw this piece three more times, right? It's going to be CH2. Then you'll have CH, Cl. Then again, so it kind of becomes repetitive, but that's how it works, right? Apparently, when you do the polymerization. So let's imagine that those used to be the red electrons. So now they will be here looking outwards, but they still belong to the carbons, right? So that's it. So red, 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 red on the carbon, and they stay on the carbons, right? So then you'll have the same thing on the second molecule and on the third, right? So here you go. So then you are going to make the bonds. That's your sigma bond, sigma, and so on, right? So, and then what you can also legitimately show is just kind of show the parentheses here. And now you are going to have like squiggle and squiggle here, right? So it means that these red electrons, which are called like terminal electrons, right? Like terminal illness. So they will be attached to something else, right? So like maybe, but it's going to be the next step in the polymerization. Don't worry about that. But in general, you will have this like thing. If you can show this kind of chain of the connected pieces, right? So then it's going to be kind of like good. That's where we will stop in terms of polymerization. So you can do it with some other alkene, maybe just for fun, right? If you consider that fun. So instead of Cl, show phenyl, right? Show the aromatic chain, aromatic ring, or maybe something else. Instead of like this chlorine, show the methyl or ethyl. And then just kind of like for your practice, show the polymer, right? And maybe do it not with three, but with five, right? Five molecules with a group different from Cl here. Okay, so now that's it for this part. Now we have some time to take a look at the further topics, which will be part 4, right? So in this situation, we are going to move on to the aromatic compounds, right? So let's take a look at them. Here we go. So maybe let's just start with a review question, and it will be pretty straightforward. So it's going to be like similar to what we might have on the exam, or maybe we did have this on the exam already, who knows? But what should or what must aromatic compounds have, right? Compounds have. So that is going to be the question here. What about the aromatic compounds, right? Let's try to like remember that. We did look at them in the past. So now it's going to be kind of the time to look at the details related to those compounds. But maybe we remember something, right? So that's kind of like was distinguishing the aromatic compounds from alkenes, for example, right? So that is what we saw in the past. There are some similarities between the alkenes and aromatic compounds, but at the same time, they are quite different, right? So because when you have a specific requirement for the compound to be aromatic. So let's take a look at that. And then we'll be able to hopefully get done 2 more activities, right? So as we look at the slides. All right, so the alcohol dissociation is still pending. So yeah, if you have some sort of realization how to dissociate an alcohol, you can like give it a try. So yeah, that is kind of like on the back of your mind, perhaps. So yeah, but again, it is very similar to dissociation of water, right? And then yeah, you can like earn easy points here. All right, so and now let's take a look at the aromatic compounds. Okay, well, we have quite a bit of responses going on. Thank you for your effort here. So we need to have a cycle, right? So and alkenes. That's like one way to look at that, right? So it's like a very kind of like a specific way to describe it. So, but again, we need to have the cycle, right? So then some people are like more specific and say it's going to be like a double and single bond pattern, right? So they will have to, and then somebody chimes in and says they have to alternating double and single bonds with 6 carbons. So that's pretty much where we are at, right? So that's like a very close response here. So for the aromatic compounds, that's what we indeed must have, right? So basically, it all starts with the ring. So here we show the like truly expanded structure, right? So later on, you'll be able to see something like that for the aromatic compounds. Kind of like don't be like startled, but that's what you will see, right? So this must be recognized as a 6-membered carbon ring. So that's going to be your band, and so on, right? You have like 6 bands, right? So in each case, you'll have the carbon here, right? So 6 carbons, right? So then clearly each carbon has already like 2 bonds engaged, right? But if you look at this compound, this is going to be just cyclohexane, right? So this is going to be like a cycloalkane to begin with, right? So, but then something happened, and then this thing took place, right? You are going to have the double bonds now. So, which, as at least one person mentioned, will be kind of like going here in this alternating pattern, double, single, and so on, right? So that's it. So that's going to be your like first representative of the organic like aromatic compounds, and it's going to be called benzene, right? So that's your benzene, which you can see on the slide. So this one is a skeletal structure. This one is expanded, right? So sometimes we can show that kind of like those bonds can be located not only, let's say, between specifically these carbons, but between this carbon and that one, right? So you can show like a slightly different sequence of the double and single bonds. So another way to show benzene is going to be like this, right? So yeah, basically it kind of implies that you will have the like uniform distribution of the electron density, right? So that's what that ring stands for. But for our intents and purposes, we'll mostly be showing benzene as such, right? So as it is represented on the white piece of paper, right? So, and again, it will boil down to this like pattern, as you said, of the alternating double and single bonds in the hexagon. So, yeah. So like what else can we see here? So turns out that there's going to be different like lengths in the bonds, right? So the single bond is about 154 picometers. So double bond is a little bit shorter. And then this like a benzene carbon-carbon bond is in the middle, right? It is 140 picometers, which kind of like is the result of this uniform distribution of the double and single bonds around the ring. So it's a combination, as they call it here. All right, so now let's take a look at some more stuff, right? So each carbon, if you look at that benzene structure, is going to be sp2 hybridized. So it will have this like trigonal planar structure. So and turns out the like pi orbitals on each carbon like form the 2 clouds, right? So like above and beyond the benzene rings. So that's what was determined kind of experimentally, but now we can see this like a representation of the electron density, right? So of the benzene ring. So that's going to be just like a fact, right? So maybe it will be used in the future, maybe not, but for now we just need to kind of think about like various things, right? Okay, well, we have the 2D shape. Very good, right? So, but that's what the 3D shape looks like in terms of how the electron clouds are represented in the benzene molecule, right? Then we have the sp2 hybridization, because you can, if you look at this like structure here, then you will clearly see each carbon, and it's kind of like double and single bonds, right? And then you need to be able to determine that it is indeed an sp2 hybridized carbon in like each case in the benzene molecule. So each carbon is going to be the planar. So together you will have like 6 trigonal planar carbons. and then the entire molecule will become planar as a result. So now let's take a look at the derivatives, right? So that's what's going to be kind of more related to our practice, right? So because we are concerned with the like structures at large, right? Maybe not so much of the like how the like electrons are distributed exactly. So, but now we are going to look at the chemical properties, right? So it's going to be the bulk of this like topic as well. So, and where the reactions come from is going to be the substitution of benzenes. So if you look at basically the benzene, so it is C6H6, right? So, but now we are going to have the benzene derivatives, right? So let's take a look at them. So maybe we can show here. So, well, we know still here in this structure, we can see 6 carbons, right? So, but also we are going to see less hydrogens. It's going to be only how many? 5 H's, right? So basically it means here, if you compare it with benzene, which used to be that, right? So you remove one of the hydrogens and you substitute it with a chlorine, right? And now you have the so-called chlorobenzene, right? Basically show the name of the substituent, and then it follows the name of benzene follows, right? So here, same thing, right? Bromobenzene looks like that. So then next one, we have our new terms, which is going to be, for example, here, this guy, right? What's that? That's from the past, right? It's going to be the alkyl chain, which is present in ethylbenzene. So then you have NO2. That's another functional group to remember. So nitrobenzene can be made if you remove one of the hydrogens in benzene and switch it to NO2. You will get the nitrobenzene. Then, okay, so next, some more compounds. So those ones will have to be memorized because they are kind of like foundational things from which we can build something, right? So such as, for example, toluene, looks like that, right? So phenol, aniline, and benzoic acid. So those compounds are already present in the activities, right? So, and then we are going maybe to take a look at them. Here, so if you want to like have more information about those compounds, you can do that, right? So that will be like the question, okay, what can we add to those compounds, right? If you look at toluene, so it will like stay as is, right? So if we move on to phenol, so show the spelling here, right? So it's going to be O-N-O-L, phenol. So just kind of like pay attention to that because there is going to be one other compound which will sound very similar to phenol, but it's going to become a little different structure, right? So just FYI. So again, spelling is going to be kind of a big deal in general, right? So as you move like down the line in your careers, so this will become like an important piece, right? To be able to spell those names correctly. So then here you can show the famous lone pairs, right? Which is what many people reflected in their challenge assignments, like for like exams, right? So then we are going to have two lone pairs on the oxygen, right? So then you will have like one lone pair on the nitrogen. And finally, we have here the benzoic acid, which will have 2 lone pairs here and 2 more lone pairs here on that oxygen. So that's it, right? So now we can kind of see what we like here, something that we saw in the past already, right? Such as, for instance, acid-base reactions, right? So aniline has this NH2 group, which is an example of the base group, right? So how will that react with, let's say, HCl? Well, you need to be able to show that because honestly, it was already on exam 1. Even if it was like bonus point question, it will come back anyway, right? So now we have benzoic acid. Okay, well, you used to have maybe some sort of like simpler acids, right? Such as, what's it, acetic acid, right? Acetic acid, you will still have like COH and methyl attached to this like a carbon with an asterisk, right? So let's say if we have this carbon with an asterisk, So let's just mark it as such. And now we can have maybe a very simple acid that will be looking like this, right? So that was basically our exam one, this black compound there, right? It was acetic acid, basically found in vinegar, right? Whatever vinegar you use, like white vinegar, maybe some kind of like Chinese black vinegar. So you can still find those this acetic acid there, right? So now you are going to like make a switch, obviously from the methyl, right, CH3. You have a switch to this C6H5 ring, and now you have the benzoic acid, right, which is going to be like a very like first representative of the aromatic acids. And then if we imagine, we can like have many more derivatives of the benzoic acid. Then aniline, well, what is that, right? So just to kind of try to relate it to some common things. So we used to have NH3, right? Which is ammonia, so NH3. Now you remove this H and switch it to C6H5, or this kind of like benzene ring, and now you have the aniline, right? So that happens to be kind of like a compound, which is a big deal because it can be used as a starting material for like various like chemicals that you can synthesize, right? Maybe some dyes or drugs and so on, right? So that's going to be kind of like the premise here, which is served for activities, right? So, and here we go. So, and then also like phenol. Phenol is an alcohol, essentially, right? So, because you have this like a COH group, so, but it's going to be an aromatic alcohol because it is because you have the OH attached to the aromatic ring, right? So now kind of those terms come together kind of in more complicated ways, so to speak. All right, so now let's see, right? So aniline can be used as a base. So, and an acid, apparently benzoic acid can behave as an acid, right? So what can we be concerned with here? So let's take a look at some kind of like details about those compounds. They will come to us eventually. So, but like, why not to look at them right now? Okay, so let's see. So here we go. So that's going to be about the chemical reactions, right? So like, since we are concerned with the chemical reactions, that's going to be the big bulk of this course. We might as well start here, right? So previously, like kind of like entry number one, it is the famous water dissociation, right? So you have HO, H. So I'm showing this bond because that's what dissociates in the water. Maybe let's show like several times, right? Because why not? So here you go. So you're going to make HO. So you will show the lone pairs, right? That's the original ones. Then you have the new lone pair because it's made of those like purple. Hopefully the purple color is visible. Purple electrons now reside on the oxygen, right? Both of them. And eventually, oxygen got a negative charge because it obtained an extra, as we showed with an arrow. This purple electron moved and joined the original purple electron of the oxygen. Now you have the negative charge on the OH. That's how the hydroxide is formed, right? So a very famous particle. So then next one will be hydrogen with a lost electron. In other words, consequently, you must have H plus. Right, so that's what we are going to obtain upon the dissociation of water. So the alcohol question, right, was up for grabs. So just think about this green hydrogen as some sort of alkyl. Just literally think about it as isopropyl, right, if you like this term, right, or something like that. So here I'm not gonna like think about this hydrogen as isopropyl, but rather as C6H5, right? Okay, well, no big deal. I'm going to show the C6H5, which will be, this is benzene, C6H6, right? So now I'm going to remove one of those hydrogens. This hydrogen is gone. And now I'm going to switch it to OH, right? That's it. And now if I'm asked the question, please show the dissociation of this alcohol, I will be looking, okay, this is copied here, right? So that's it. So basically, this part is now dead. And then I literally need to kind of redraw all that stuff, except instead of this hydrogen, I will show the benzene ring, right? And then literally like this is like the bond here as well, technically, right? So then O, copy paste the dots. So you will have your like anion, right? And now add H plus. So that's going to be your dissociation of the alcohol, right? So like very similar to dissociation of the water. So that's like what it would be for the alcohol that your peer actually drew on the board previously, right? So, but here we have another alcohol, which is phenol. Okay, so now let's take a look at maybe at the future questions. So we have activities, right? So for the remainder of the time, and then they will be about, so let's just do the dissociation for now. So it will make it a little bit easier, right? So we'll have the here benzoic acid and the phenol, right? So well, oh no, aniline and benzoic acid, right? So as we can see here, so aniline acts as a base, right? So benzoic acid acts as an acid. So you have a chance now to show the base behavior of aniline and the acidic behavior of the benzoic acid, right? So that's up for grabs. So let's maybe try to do that. So I'll add some prompts that you can use. So maybe let's imagine that aniline reacts with HCl, right? So, and benzoic acid, just dissociation. So that's like what we want to show here. So benzoic acid, dissociation, right? So again, you did see dissociation of the carboxylic acid in the past. So like nothing new will be here. So at this point, it's just going to be the review question. So, and then if you want to give it a try, then you might as well show that, right? So the key element in the acid will be this like OH bond dissociation, right? You see that here, so it's already kind of like we show the dissociation of the OH bond multiple times, right? It will be the same in the acid, right? So just kind of in a slightly different structure. So then for the base behavior, right, which we'll be looking at like, again and again, so you will have something like that. So maybe it's going to be the third prompt. So if you want to use NH3, right, let's say it reacts with HCl, because why not? So you have the lone pair here, right? So now you are going to make NH4, right? So this pair will be gone, and then you will have the Cl minus. So we might as well try to kind of apply this principle to aniline, right? So which will also have the lone pair on the nitrogen. It's just going to be a little bit different of the structure that you'll need to draw. Okay, so yeah, again, like easy 3 points. So you have all the prompts here, right? So how the OH group dissociates, how the ammonia reacts. So, and instead of here you have NH2H. And in your case, aniline, you have NH2 with the ring, right? So with the aromatic ring. So that's all it is. So like literally only one switch. And then the good news is that kind of those rings, just leave them alone, right? So they will not react in the course of dissociation. So yeah, okay, well, we have one candidate. Good job. So finally, so we have two chances here, right? So we have the aniline base behavior and the acid. So yeah, you can choose anything you want. So because you're the first one. What? So I did this page. So you don't have to like think about it right now. So let's just show the this yeah the base behavior. All right, so that's maybe a reminder, colors, and yeah, take it away. All right, so let's take a look at whatever we look at right now. So I think it's going to be aniline, I assume. Right. Okay, good job with the expanded structures, right? So if you go with the expanded structure, like don't forget your hydrogens everywhere, right? So that's going to be like a great thing to have, to say the least. All right, great. And we have it here, plus HCl. All right, great. So now we just need to correct the number of hydrogens. So aniline still has NH2, right? Yeah, great. So now you add, yeah, just one H becomes NH3. Okay, great. So finally we made it, right? So we have the salt, right? So, and we have the base behavior here. So that's an example. You will see that like several times. So now we have the famous carboxylic acid. So if anybody wants to give it a try, so that's going to be again easy 3 points for the next exam. So granted, you did it in the past for the bonus point question on exam number 1. So we still have this available. So, okay, great. So yeah, let's do that. So historical things, right? So now we have the benzoic acid, right? So which will be, for which we'll need to show the dissociation. All right, so let's go ahead and do that. Let's see what's happening with the ionization of benzoic acid. Okay, very good. So you can draw any structure you want, right? Skeletal, expanded. Yeah. Okay, so this is going to be our alcohol, right? So which is show the double bonds if you or yeah, like whatever you're doing. So go ahead and do that. Yeah. Great. So you did the advanced question, which is great. So now we're going to show the reaction, right? So with the KOH looks like, all right. So that's good. So yeah, that's a good effort. So that's awesome. Let's see what we are going to obtain here, right? So the OH bond will be broken. So we'll have the O minus, right? So and then we need to decide with what it's going to associate. All right, great. So we're going to make the OK bond, right? So because it is O minus and K plus technically, and then we're going to obtain the water. Okay, well done. So awesome. So yeah, that's great. Okay, so and now, yeah, so at this point we are done. So we're going to continue on Tuesday with the this slide nomenclature, and we'll see where we're going to finish on Tuesday. Right. So if you worked on the board, please stop by to drop down your names. All right, and bye everyone.